Alright, what's going on, folks? Welcome to electricity class. Let me get the video camera started up so you can see my pretty face. And we're going to cover this stuff. And we're not going to get too super heavy duty into this thing. I'll probably cover sections 20-1 through 20-3 and not go on to 24 yet. Yeah, let's just stick with that for now.
Charles, we both put new Dropboxes. The one I used, yeah.
You're right. I forgot. I didn't do that. No. The answer is no, I didn't. I'm sorry. I better get on that and do that right now. Or let me do that right after I'm done with class. Is that cool?
Okay. Yeah.
All right. Because I also need to reassign homework and put up new Dropboxes. I'm not being very good with that stuff. I'm just kind of worried about the content so far. So I got a little PowerPoint. It's a pretty little PowerPoint. And we're going to talk today about this thing called electric potential and electric potential energy. Now, I know that Austin and Tiger, and maybe even you, Victor, have had this concept before, but all right.
I can't hear you. I'm getting a lot of feedback from the side.
One second, I'm sorry. Participants. Is that better?
Yeah, but now the video dropped.
The video dropped? What are you talking about?
Yeah.
Oh, okay. Alright, now,
it's on my end.
the problem is I think that Kalena lives on an airfield. So the jets, was that a jet in the background, I'm assuming? Austin, Kalena, you don't need to talk, you guys can chat it to me. But I figured that there's probably like a jet landing on top of them. So so it gets a little loud. I'm sorry. I'm gonna have to turn you guys off for now until the jet passes at least. Then we can get started up on this. Anyway, you know how we had this analogy between gravity and electricity, and we used that same equation. Actually, it wasn't exactly the same equation, but it was very similar. Well, we're gonna have the same kind of deal when we're talking about potential energy and kinetic energy. And you guys are like, wow, there's a lot of these good, connections that kind of go back and forth. I think that's really exciting. So when we're talking about all right, so once upon a time, I talked to you guys about the potential to do something. Now, if I take a book, a heavy book, and I hold it over my head, can you see the book? And I hold it over my head, and it has the potential to do work, right? It has the potential to, if I'm just holding it here, it's not moving. It doesn't have moving energy. It has potential energy. It has the potential to really hurt me, right? Yeah, to drop on my head. Exactly. Good. Very good. Now, going back to that, remember that I was showing you guys about the contour maps? And we had a map that kind of looked like this.
Yeah.
And we were saying, okay, well, now here's the contour of some kind of cliff or something like that. And if I were to put a tire right here, but say I didn't move it, I'm just holding the tire right there. It actually has, well, the reason why I originally showed you this contour map is because I was showing you how electric field lines work. How we're talking about, like things that look like this. In essence, those are contour maps. That's what they are. They're contour maps. But let's scratch that. And let's talk about the contour map. Let's go back to an actual physical, tangible thing that we can hold. Imagine if I held a tire right here. That has a potential energy, right? It has the potential to roll down the hill. Do you guys agree?
Yeah.
And if it's closely spaced together, that means it's very steep, and so therefore it has a lot of potential to roll down the hill. Versus if it's like kind of spread out a little bit, it has less potential because a tire right here will roll faster than a tire right here. You guys see what I mean?
Mm-hmm.
And when we're talking about like the potential energy of something, we're talking about the energy of we use the equation E, and we call that the electric potential energy, because here's kind of how I think about it is, imagine if you have a positive charge here, right?
Okay.
And you put another positive charge here. Now you put a nail in this one right here, and so you lock that guy down. What is this one on the right side going to do?
Move all the way to the right.
It's going to move to the right, right? It's going to repel.
Yeah.
It's going to go away. But say I put a nail in this one too, and it doesn't get to move. Well, it still has that energy that you know what I mean, because it's associated, because it's repelling right now. But it's not moving, so it actually has the potential to move. Does that make sense to you?
Yep.
So, like, if I were to draw the electric field lines of just that point charge, it would look like that. And then if I had another positive test charge that I put in there, that now has a potential, because it has the potential to move. Now, here's what we do with electric potential. Like here's kind of what we're going to talk about in this chapter. You guys ever use a camera? And you guys ever use like the flash on a camera?
I try not to.
Let's talk about like a little bit older cameras, because like the iPods don't really use flash, and the iPads don't use flash, and the iPhones or whatever. But like the old cameras, they used to go like this, and then you would like flash. You guys ever hear that? Like the battery would charge up the thing.
Yeah.
What you're doing is you're building a potential, or here's a more recent development is, have you ever heard of a AED, or a artificial external defibrillator?
Oh, yeah.
Like you ever see on the doctor shows where they go clear, right?
Yep.
What they're doing is they're charging up the plates and then releasing all of that energy. Well, that charging up the plates is building up this electric potential energy. We cool?
Cool.
So when we talk about electric potential energy, actually we don't use the symbol E, we use the symbol U. And that's actually similar to a symbol I used when I was talking about gravitational potential energy and kinetic energy. I remember very quickly introducing that to Austin and stuff like that. So what we're going to do is we're going to talk about, well, energy is actually related to this concept that we call work. And for example, this cup now has energy. See, it's being held over my head, or it's being held up in the air. It has energy. It has energy to fall. Where did it get that energy? Well, my hand did work on it. Its work is force times distance. Exactly, Austin. Work is equal force times distance. Well, in our case, work is equal to force, but what is force? Force is actually Q naught E. I remember teaching you that equation. And the distance is D. So the equation we're going to use is work is equal to the test charge times the electric field times the distance. And where does the negative come in? Well, the negative comes in from the fact that like charges repel and opposite charges attract. So we have to kind of take into account that thing. So that's why we threw in that extra negative. Are we cool?
Yeah.
Okay. Now what we're going to do is, if we're talking about work and we're talking about how work is equal to Q naught E over D, we have to introduce this concept of a test charge. But this concept of a test charge is a little weird because that means I have to throw in a test charge every time I want to define the work that, or the potential energy, the electric potential energy that it has. So instead of defining the test charge, what I'm going to do is I'm going to get rid of the test charge. In order to do that, I divide it by Q naught. You guys agree?
Mm-hmm.
Hey, what's going on, Asia?
Hi.
All right.
Struggle is real.
That's good. All right. And since if I divide by Q naught, this part right here is how I define delta V, which I call this, my friend, is what we call the electric potential energy. So it's equal to actually negative W over Q naught. And how do we measure this thing? I'm sure that you've heard this before. We measure it in volts. Have you ever heard of that unit before?
Yeah.
That's what a volt is. It's the amount of work this thing would do divided by the charge of your test charge. Are we cool? Kind of. Yes. No.
Kinda. Could we summarize that in simpler terms?
Well, actually, fine. Here, I'll tell you what. If I do a problem for you, then it becomes like, oh, I get it. It's kind of easy. And why don't I summarize it because Asia just got in, so it would be good for me to kind of say like, hey, I'm going to kind of wrap this. I'm going to try to like catch you up on what we're talking about. You haven't had physics before. Have you ever had? All right. You know what? Let's take the time to talk about this. Because Kalana, do you get it, or should I like go over it a little bit some more? All right. Okay. I'm going to try to explain it. All right. So what I didn't cover with you guys once before, and I covered with the physics class, which is why I think that everyone who takes electricity should have had physics beforehand. But anyway, so you didn't have physics beforehand. There's this concept that we talk about where we talk about energies, okay? And one of the types of energy is called potential energy. It's like if I have this cup. Come here. If I have this cup and I almost dropped it. If I hold it over your head, right? Is it hurting your head? But if I drop it,
It'll work.
it will hurt.
Yeah.
So it has the potential to do something. Okay? And where does that energy come from? Well, it comes from gravity constantly wanting to pull it down and me holding it over your head. Now, if I stood up, in fact, if I stood all the way up on this swivelly chair, I actually fell down on this chair this morning, but if I stood up all the way up and held it all the way above my head, does it have, what kind of energy does it have?
Potential.
It has potential energy, but what's the difference from me holding it like this?
A lot more of it.
It has bigger potential energy. So the more height you have, the bigger potential energy you have. And that's when we're talking about the specific one called gravitational potential energy. Does that make sense?
Yeah.
Now, when we introduced this concept of a contour map, do you remember that one right here? This contour map, like say this were a cliff, and say that it comes all the way up to a point, so this maybe like that. And I put a tire over here and a tire over here. I could see by the contour map that since those lines are closer, this one is going to move faster than this one, right? But in essence, what if I say I didn't drop the tire yet? It's not moving, but I'm actually just holding it right there along the edge of the cliff. Then you would say, oh, it doesn't have like moving energy, which we call kinetic energy. It has this idea of potential energy. Well, the same thing happens with electricity. When we have like a positive charge right here, and say I put a nail in it, so I nail it down, and I put another positive charge over here, and this is just the test charge, he would move to the right, right? Since they're both positive, they would repel. But I put a nail in him as well, and so they're both kind of stuck there. Then we would say, okay, this thing has the potential to want to move like that. You know what I mean? And the way I introduced this is I said, okay, well, what's going on is when you use a defibrillator or a camera and it charges up a plate and then it like explodes the energy like a defibrillator. Do you know what a defibrillator is?
No.
All right. If I pretend to have a heart attack, I have a heart attack. Then you would go to the wall and you would see this thing called an AED. You'd pull that thing out, you would charge it, you would press charge, and it would go beep, and you would say clear, and then you would put these paddles on my chest, and you would go boom, and it would shock me back to life. And actually, that electrical impulse would give me enough energy to jolt my heart to say, "Oh my gosh, I'm up, I'm awake, you know." That thing saves lives. But that's what we're talking about here. We're talking about something that will charge up and it has the potential to move, and then it moves. You know what I mean? But that's what you're doing when you're charging it up. You're building up all of that potential in there to move, and then you let go of the nail, and it goes pow. That's exactly how it is. Is the friction of rubbing the paddles what causes the electric pulse? No. They only rub the paddles so that it's not so cold when they put it on your chest. But then again, if you're having a heart attack, that doesn't really matter, does it? I mean, like, if I'm having a heart attack, I'm dying. I don't mind having cold metal plates on my chest. But I don't think that it's that they have to go. They just press the button and it goes, and they go. Pow. You got it? So it's not like, hey, I'm going to make friction. Clear. You know what I mean? That doesn't do anything. See, watch.
That's a lot of static electricity there.
I know. You feel anything?
No.
Okay, all right, just making sure. All right. But I love the question. It's great. So it's already charged. No, it's not already charged. It's kind of like if I want to build a device that will knock Aisha out when she walks in the door, I could hold this cup up really high all the time. Right? But that's kind of dumb. That wouldn't really work. So what I'm going to do is, when she walks in the door, I'm going to go, clear, boop, and I'm going to raise it up and then drop the cup. You know what I mean? I don't want to hold all of that potential energy in there because it's just going to start to slowly dissipate. My arm is slowly going to start to get tired. That's why your camera flash doesn't just go, when you shoot your camera and you're talking about like one of those nice cameras that have an external flash, it doesn't just go boom. You know what I mean? It actually takes some time to charge up and then flash. And then why can't you just go boom, 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 boom? You guys ever do that? Like I have my Canon A1, which is a pretty good, or not an A1, but I have a Canon Rebel, which is a pretty good camera, right? And I'm going boom, and I'm like, come on, take another picture. Come on, figure it out. And then it says busy. And I'm like, come on, take it. And then it finally takes another picture when it's like I missed the opportunity or whatever.
Yeah.
And what happens is the plates are charging up, and they need to charge up enough to get that flash out, but then they need to recharge, and that's why it takes so much time. If you had a super awesome battery to charge up these plates real quick, you could go. And that's why you see, like in the sports stadiums, they have all these dudes with these big cameras, and they go. But then again, they have these fanny packs with basically batteries. That's all they are. They're just giant batteries.
Those are like separate flash canisters.
Yep. There's separate flash canisters that help you charge up the thing. So anyway, what we're talking about is when we talk about energy, we talk about this concept of work. That's really what energy is. It's work. It's the force times the distance. And we've learned before that force is actually Q times E, the electric field. You know what I mean? How much force is this guy going to feel on him? It's Q times E. And so we said, oh, well, if we want to make it work, all we got to do is add in a D. There we go. And then I throw out this idea of there's this negative out in front. Where does that come from? Well, that one comes from, if you actually, like, I know this one was a little bit funky for me to really wrap my head around when I first learned this. And I'm still trying to, like, explain this to everybody. But essentially, because I have two positives right here, and if I do this, if I decrease the distance, if I, like make the distance smaller, so I make, D negative, the distance is negative, the work will actually the work will do what? It was bigger or smaller?
Bigger.
The work gets bigger, right? Because there's more potential, it has more potential energy stored up inside of there. So if I make D negative, then the work should be positive, so that's why I have that extra negative in there. The basic concept is because opposite charges attract and like charges repel, that's why I'm going to have that, throw in that negative in there. And the way we measure, now we don't actually just do straight up work with this stuff. We actually, having a Q naught in our equation is a little weird because that means it depends on the charge that you're talking about. So we divide by Q naught and then we define this as the electric potential energy. So potential energy obviously applies to gravity, and we talked about that, but potential energy now applies to this concept of electricity. And the way we measure electricity is in volts. After Alexander Volta, who basically made he didn't make the modern day battery, but he made the battery that was before the modern day battery. So way back when. And he lived back in 1745 was when he was born. So this was almost 200 years ago. Like that. Almost 300 years. Well, 200 something years ago. That's pretty bad to the bone. Like this guy's playing with electricity and stuff like that 250 years ago. I don't know. I think that's cool. All right. So what is a volt? The units of volts. 1 volt is equal to. Do you guys remember what?
What is E over D?
What is this one right here? ED. Is that what you're asking?
Yeah, ED. Yeah.
Q naught ED is actually work. W is equal to Q naught ED. Right, I have that equation right up here. W equals Q naught ED.
Oh. The work is the effect of
Work is
the
force times your
energy.
distance, and the force that we're talking about is the charge times the electric field. Didn't we cover that? Force is equal to charge times the electric field? I thought we covered that in chapter 19.
I'm sorry, the internet's really slow. I can't hear anything you're saying right now.
I thought we covered that in
Yeah.
chapter 19. The force is equal to charge times field. Didn't we cover that? If we didn't cover it, I'm sorry. I apologize. That must have been a real jerk move by my part.
But I can't even.
Oh, okay. All right. Let's see. Force is equal to this. Electric. All right. Yeah, we did cover this. We said, I know this equation. I gave it to you. It's electric field is equal to force over Q naught. I know I covered that for you last time, right? So, force is equal to electric field times Q naught. Right?
Yeah.
So if work is force times distance, then in order, this equation right here is work, which is why I have Q naught ED. Does that make sense? We cool with that? Like it's nice because it all comes together. But here, let me show you what's going on. All right, let me talk about what a volt is first, real quick. What is work measured in? And Austin knows the answer to this, and I don't think you guys know this measure. The answer to this.
Watts.
No, it's not watts. It's actually joules.
Joules.
Do you remember that, Austin? And a charge is measured in. Now I know you guys know this one. What does a charge measure? What is a charge measured in?
Coulomb.
Coulombs, exactly. C. So 1 volt is W over Q naught, which is actually a joule over coulombs. That's what a volt is defined as. We cool?
Yeah.
All right. So, do we always use this? Well, no, not really. sometimes we use electron volts. And that is not really a useful unit when we're talking about like actual components. We usually talk about volts, you know, like not 12-volt battery, a 9-volt battery, you know what I mean? But when we're talking about electron volts, what we're talking about is like the charges on electrons. When we're talking about things at the atomic level, that's when we talk about electron volts, and that's a much, much, much smaller unit. Because all that is basically, what is an electron volt? Well, an electron volt is simply, hold on 1 second, coulombs times volt. Yeah, electron volt is basically the charge that you have on one electron. So that would be this guy, times your voltage, times 1 volt, which is a really small number. Are we cool with that? Alright, here, let's do this one. Let me see, my PowerPoint I had up was here. I talked about how electric energy is that. Energy is conserved. Did we get to that idea? No, we didn't get to that yet. We got this thing right here. I covered this equation with you. We covered how the volt is actually, the definition of the volt is work over the charge. And then we got to talk about this stuff. Energy conservation. All right, cool. All right, so check this out. Here's what's kind of going to go down with this. Let's do an example problem. Say that we want to find the charge in potential energy. So find delta U as a charge of 2.20 times 10 to the negative 6 coulombs. So that's a Q equals that, right? Moves from point A to point B, given the electric charge. Where's point A and point B? That's a dumb question. All right, well, we know that delta U equals Q naught delta V. Did I give you that equation?
Wait. What's delta? It's delta U, what's delta V, what's Q naught, and delta V.
Oh, okay, I got it. Here's what it is. It's saying that the work is equal to Q naught delta V, so they're asking you to find the work. Right? Or, here, this is how I told you the equation. Delta V is equal to negative W over Q naught. So I can just multiply both sides by Q naught, and then there we go. Cool? And they told me in the problem that the difference in voltage is equal to 24 volts. So apparently if we put this on a 24-volt battery or something like that. So all we do is if we want to find the work for it, we just...
I can't hear you again. I can't see you either.
All we do is if we want to find the work for it, can you hear me now and see me now? Hello? Can you see me now?
I can hear you.
All right, well, hearing me is fine. Can you see the computer screen? Don't worry about seeing my face.
Yeah, no, I can see the computer screen, yeah.
All right, good. My face isn't really that important. All right. All we do if we want to figure out what the work that, this thing underwent by moving this charge from across 24 volts is we just multiply these two. So I got delta V times Q naught, which is equal to 24 volts times 2.20 times 10 to the negative 6 coulombs, which is equal to my work. And so that's equal to 24 times 2.2, which is 5.28 times 10 to the negative 5 joules. And that's the work done. Are we cool? Yes? No? We good? Alright, cool. Alright. They asked for another one. they said, all right, well, what if we made this? What if we? Well, I don't know. That one's a little bit boring. It's basically doing the same thing. Okay, assistant faults. All right, let me read this one. Connection between electric field and energy straightforward use of okay. Divided by delta S. All right, let's do this one. Ready? We have 2 plates that we set up. Cool? And I take these 2 plates and I attach a 12-volt battery. So I got a 12-volt battery. Kind of like this. And I usually label it like this, positive, minus. So this guy's connected to the positive side, that guy's connected to the negative side. And there's these plates are getting charged. And what's the charge in between them? Or what is the the voltage in between them? That would be 12 volts. We cool? Now what's going to happen as I charge up this plate? Well, the positive side is going to build up over here, and the negative side is going to build up on here. Because this one's connected to the negative side, and that one's connected to the positive side. Are we cool with that? We good? All right.
Yeah.
Now, if I put these plates next to each other, all right, what would the electric field lines look like? That's my question to you. If I put a test charge right here, what's going to happen to him? A positive test charge.
Going towards negative.
He's going to go straight down. Do you agree?
Yeah.
And he's going to go straight down, and he's going to go straight down, and he's going to go straight down. The electric field looks like this. Are we cool? But now what we'll do is we want to calculate, well, how big is that electric field? And the size of that electric field...
Wait, so all our test...
What is that?
Wait, are all our test charges positive?
Yeah.
Can they never be negative?
Our test charges are positive. So, by the way, I need to give you this equation before I give you this example. I can relate the electric field to the voltage very nicely. Electric field and voltage are related very nicely to each other. My change in my electric field is equal to my change in my voltage divided by the change in distance. And I put an S because I don't want to put a D because there's too many things that are labeled D. So distance. So if I want to figure out what the change in electric field is, you have to tell me how far apart they're spaced. And the problem says that they are 0.75 centimeters spaced apart. We cool? So all you do is if you want to figure out the electric field, you just take the voltage and you divide it by S. Okay, fine. The electric field is the voltage, which is 12 volts, divided by 0.75 centimeters, and you end up getting well, let's see. I want to make that, instead of centimeters, I need to make that meters. So that would be 0.0075 meters. So that's equal to 1,600 volts per meter. That's the electric field of this thing. We cool?
Yeah.
Now, say that that is like, I guess a way to think about it is that's like that's like the amount of gravity that we're talking about. This is the electric field kind of represents like remember when we were looking at the contour maps? The electric field, if it's a big value, that kind of represents like the steepness of the slope of the cliff that we're talking about. If it's a big electric field, basically if I had a big voltage on here, I would have a big electric field. Does this make sense? All right. If I have a big voltage on here, I would have a big electric field. Why would I need to know the electric field? I'm basically figuring out how much potential this thing has. You see what I mean? Okay. All right. basically, if I have a big voltage, that means I have a big electric field. That would be similar to having a contour map that has a very steep slope. The bigger the voltage, the bigger the hill, therefore the bigger the slope that we're talking about. And that means that a test charge would zoom past here. So I need to know the not only how the electric field looks, and we did that last class, but the size of the electric field. Now, if I move these plates closer to each other, what do you think would happen to the electric field? All right. If I move these plates further away from each other, what would happen to the electric field? It won't zoom everywhere on the field depending on the position of the charge relative. It would get bigger. Actually, no. If I move these plates further away from each other, it would get smaller. It's harder for that thing to jump across, right? It's harder for that. The force would be smaller, so the electric field would be smaller, and that you can actually see that right here. If I make S bigger, what happens to the electric field overall? Well, since S is in the denominator, the whole electric field will get smaller. We cool? Like that kind of goes along with what your intuition is. All right, so here let's try this then. What is the electric potential energy, which is the delta U, which we call W, is equal to the Q times delta V. What is that if I use a charge of 6.24 times 10 to the negative 6? Okay, well all you do is just plug that into there, and that's 6.24 times 10 to the negative 6 times 1600. Actually, no, not 1600 volts per meter. This is 12 volts total. And you multiply those two together, and you end up getting you end up getting 7.5 times 10 to the negative 5 joules. That's how much work is done on that. Are we cool? So potential energy is directly connected to the distance of the field. Okay, wait. Victor is saying wait what? Wait for what? What is it that you're confused about? And I might admit to you, or actually I totally admit to you, if I botched this lesson. Oh yeah, I'm sorry, this is part B. Part B. This is part A. Are we cool? If I botched this lesson, like I totally made this confusing topic even more confusing to you, let me know and I'll redo it. I'll do my best so I can redo it. Doesn't the force on the charge get smaller the further away the charge is from the electric field? Yeah. The force gets smaller the further away it moves from the electric field, but as we move down into this thing, this electric field right here is basically is a constant 1600 volts per meter. How do we have a perfect number? 12 divided by 0.0075. 12 divided by 0.0075 is 1600. We have a perfect number because we happen to choose numbers that are so nicely put together. Like we pre-did this example problem. All right. Here's the last thing I want to cover before we move on. Okay? And this, I think, concept will be kind of easy for you to understand. Hopefully it will be easy for you to understand. You guys ever hear that expression, what goes in must come out? What does that mean? I guess to me what it means is, like, I can apply that to food and eating. If you eat junk food, like, junk food is going to come out, and it's actually, technically, it's not going to come out, it's going to stay in your body, but I mean, it's going to, like, expose itself in your body by making you fat. Whereas if you eat healthy food, then it actually comes out of your body, and you don't need you can poop it out, and then you're all done with it, and you don't get fat, whatever. But I mean, just the same with energy. The amount Austin's saying exactly what I'm getting at. Energy is conserved. The amount of energy that I put into a system has to equal the amount of energy that comes out of a system. I can't create energy out of scratch. I can't destroy energy. Like if I take this cup and I hold it over your head and I drop it, it has potential energy now. When it hits your head, does it have potential energy? No, but it's moving, and so it turns into a different form of energy. So the energy didn't get lost. Like the potential energy just didn't disappear. It turned into kinetic energy. Are we cool with that?
Yeah.
So it's what we're saying is like energy must be conserved. That means if I add up all the energy to begin with, that would have to equal the sum, which means add up, of all energy in the end. One way to write this mathematically is to say that sigma u initial is equal to sigma u final. Have you seen that symbol before? This is the universal math symbol for add up everything. That's all it is. That's all it says. Essentially, I said it in 4 characters what I said up here. That's the same thing. It means you add up all of the, U is the symbol for energy, so I add up all of the energy to begin with and make that equal to all of the adding up all of the energy to end with.
Oh.
So in those 4 characters, I said those 2 sentences. And you read it and you're just like, oh, I get it. I mean, it's probably easier that I wrote it out like this, but I'm lazy, so I'm going to usually write it out like that. So here's what we can say is, if we have a particle that's moving, and we're talking about electricity, okay? If we have a particle that's moving and talking about electricity, this particle can have 2 different types of energy. It can have kinetic energy, and it can also have potential energy, but this time the potential energy that we're talking about is electric potential energy. Does that make sense? And the electric potential energy, U, we define as Q times V. Right here. I keep switching between the words electric potential energy and work, but it's equal to Q times V. It's actually, we use Q naught times V, but that's when we were talking about a test charge. Now we're talking about an actual charge. We cool? So if I add up all of this to begin with, that should equal to the kinetic energy in the end. So that's what the F stands for, it's the final. Plus the potential energy of A in the end. Are we cool? Does that make sense? Alright, so here, let me show you a problem, because once I show you a problem, you're going to be like, oh, that makes sense. I hate to do this to you as well. I need you to take an equation and just accept it. I didn't tell you what the equation for kinetic energy is. I told Austin, because he had physics for me, but yes, exactly, Victor. So basically, the total never changes. If I add up everything to begin with, it has to equal to the sum of everything in the end. That's exactly what I'm saying. All right. By the way, I didn't let you know this, but the kinetic energy, as Austin is saying, is equal to 1/2 mass times velocity squared. Have you ever seen that before?
Probably.
1/2 mv squared? You might have seen that before. Maybe you haven't. I'm teaching my 8th graders that equation now, but then again, they're pretty advanced 8th graders, so maybe you haven't seen it before, maybe you have. let's try this one. Let's do this one. All right, let's do an example. Say that we have a particle. How big is this particle? It is a mass of 1.75 times 10 to the negative 5 kilograms. Why is it so small? Because we're talking about like electrons and protons and that kind of stuff, and so you're talking about really small things. You know what I mean? We're talking about moving things with electricity. That's not the big things you're talking about here. All right, so we got a small little particle, and the charge on that particle, Q, is equal to 5.20 times 10 to the negative 5 coulombs. So it's a small charge. Actually, it's not that small because we deal in microcoulombs. So a coulomb, times 10 to the negative 5 is basically 52 microcoulombs. It's a little bit bigger than a regular one. But and say that we start the particle off here, okay, and it moves to another point B, and the difference in potential energy, the delta V, is equal to 60 volts. So there's you can say there's 0 volts here or 60 volts here. You can say there's 100 volts here and 160 volts here. But all I know is that the difference between them is 60. We cool? Then here's my question for you. What is it going to do? What is this thing going to do? It's going to move, right? And it's going to move from here all the way down to here, right?
Yeah.
And it's going to like speed up. It's going to zip past there. So, how fast is it going to be going? That would be a good question to ask. How fast is this thing going to be moving when it goes across that potential? All right, and let me show you how to calculate it, because once I show it to you, you'd be like, oh, I get it. All right, let's set up our equation. Let's say that adding up all of the energy in the beginning is equal to adding up all of the energy in the end, right? And then let's say this. Let's say, well, what kind of energy does it have in the beginning? Well, it has kinetic energy, right? And it also has potential energy, electric potential energy. We're talking about electricity here. So it's U of A, because this will be point A and this will be point B. So at this point right here, it has kinetic energy and it has whatever potential energy at point A. You agree? And I'm going to make that equal to the kinetic energy it has in the end plus the potential energy it has at point B. We cool? Yeah? Good? You sure? All right, awesome. Think about this. Does it have potential energy? Does it have kinetic energy to begin with?
Yeah.
Austin's saying no. Why not? Why doesn't this thing have potential or kinetic energy to begin with? Because it wasn't moving. Exactly, Asia. It wasn't moving to begin with. You know what I mean? So this, my friend, is 0. Not bad? All right. What else? I also know that UA is actually Q times the voltage at A is equal to 1/2 the mass of the thing times the velocity squared plus Q times the voltage at B. We cool? Yes, exactly, Austin. Kinetic energy is 0 at the beginning because there was no it wasn't moving. But it is moving at the end, so I can't make this one 0. I can't make kinetic energy final 0. It's moving. So let's solve this out. I want to get V. I want to get V all by itself. How do I do that? I know. I'm actually realizing that I'm probably doing this really quickly because You haven't gotten used to weird math yet. This is weird math. But when I get you used to it, you're gonna be like, oh my gosh, this is so cool. I want to get v all by itself. Do you know how to do something like this?
Yeah. You have to do the same to each side if you want.
I like it. I like it very good.
I
Here,
don't know what to
let me start you off this way, okay? All right, let me do this. Let's say 4 equals 3x plus 2. Can you solve that?
Yeah.
Okay, do it for me.
Wait, what do you want?
I want to solve for x.
Um,
I want to solve.
subtract
Kalena,
both sides by 2.
throw your answers into here, and also Victor, feel free to talk as well. What do I have to do first? I got to subtract both sides by 2. Subtract by 2. So I've got 4 minus 2. Do you mind if I just leave it as 4 minus 2? I'm not going to subtract it just yet.
And then you divide both sides by 3.
Then I divide both sides by 3. We cool? I get x all by itself. In this equation, I want v all by itself.
That one.
Yes.
Okay.
I'm going to do, here's my hint to you. It might look different, but I'm doing the exact same steps as what we did. Exact same steps. I'm going to subtract both sides by QVB. Okay? QVB. Alright, so I've got Q times VA minus Q times VB equals 1/2 MV squared. We cool? Austin's pretty much taken the whole thing and he did it already. But anyway, would it be alright, before I do the next step, would it be alright if I simplify the left-hand side a little bit? There's a Q in both of them. Can I just make it this way? Because if I distribute that Q back in, it would be the same thing as the line above. And I always like, simplifying things as much as I can. All right, let's move on. We want V all by itself. Okay, I'm going to multiply both sides by 2. And I admit to you, I didn't do that on this left-hand side, but I mean, you understand how to do that. All right, now how do I get V all by itself? I want V all by itself. Divide by M. And then square root that sucker. There's my answer. The velocity apparently is 2 times the charge times VA minus VB. What is VA minus VB? It's a number. What is it? It's a number on the screen. No, it's not the velocity. It's the difference in voltage, which I told you was 60. So all you do is just plug in 60 here. Divided by the mass of the thing, and that's, whatever that is. Square root that. All right, so you plug in numbers. 2 times 5.20 times 10 to the negative 5 times 60 volts divided by 1.75 times 10 to the negative 5 kilograms. I'll tell you what, why don't we, instead of me cheating and looking at the book for the answer, I'm going to actually do this calculation for you. Let's see. 2 times 5.20 EE, or maybe, E negative 5. Let's see if that does that for me so far. No, it doesn't know what EE is. Times 10 to the negative 5. That's what EE means. Times 60 divided by 1. Let's put the parentheses in. 1.75 times 10 to the negative 5. Close parentheses. There, that's the answer. 2 times 5.2 times that divided by that. That's your answer, but that's not really your answer, because what do you need to do? you need to square root this thing. Oh, it doesn't even know what to do. Alright, here's what I'll do. I'll take this number, and then what is the square root of that? What? 356.57. Alright, what is the square root of 356.57? Close parentheses, enter 18. So my answer is 18.9. 18.9 meters per second. That is how fast that particle is moving. Are we cool? Yes, if I use Wolfram Alpha, that probably would be better. So the potential difference, if I had, I mean, like literally, we actually solve. Okay, I see what you're saying. Wouldn't it be negative 60? And what I'm looking at is, yeah, I suppose in order to get the sign correctly, like the positive or negative, what you need to really do is look at what kind of charge that we're talking about. And then Victor is saying, so what would happen if a point was further away from the plates? Answer is nothing. You're talking about if I start a point right here and it would move that far? You're talking about that? Well, what I'm talking about is I'm actually talking about, like, let's say pretend that we're inside of the plates, far enough inside of the plates for it not to be really affected. Like, we're not talking about like, hey, I'm going to put a test charge outside of my capacitor. And a capacitor is, by the way, 2 plates. So I'm going to say I have 2 plates. I'm putting a test charge 2 miles that way. What does it do? You know what I mean? Like, we're not talking about putting the test charge there. We're talking about I have 2 plates. Let's put a test charge inside those plates. What happens? Got it? All right. Is this confusing for you, or does this kind of make sense to you? I know it's a lot because we covered an entire chapter of like physics A when we talked about energy and we talked about electricity at the same time. I'll tell you what, I'm going to stop it there, and all I did was I got through section 10.2. So read up until page 696 on that textbook for chapter 20. And I will reassign problems, and I'll make sure to I'll make sure to put up the Dropbox. And then my internet is very slow. I need to read. I don't understand anything here. Oh, Victor, I'm sorry that you don't understand the things here. I admit to you, maybe I didn't do so well with doing this lecture. This is kind of a hard concept to cover, and I think what makes it extra hard, what makes it super hard for me to cover this, is I have to remember that you haven't had basic physics before. So I'm tripping myself up because I'm like, well, I know you took basic physics, but basic physics, conceptual physics, is not really basic physics. What I'm talking about is I have to remember that you haven't had my physics part A, which is like senior level physics. Yeah, basic physics is like math, and that's actually, to me, that's like studying poetry without really understanding the alphabet. It's pretty, but it's not really like, you don't really understand poetry, you're just reading it. And I got a question, didn't you cover this in basic electricity if you had like basic physics with electricity? Or this is like just completely new to you? Alright. I'm sorry your internet's been kind of crapping out. I'm going to adjust the plan and everything to make sure I adjust accordingly to you guys, but I'm glad that you guys can make it in. Alright, I'll talk to you guys later. How are we doing, Asia?